3, 1, 2, 3. Good. One, two, three, test. 1, 2, 3, test. 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2, 3. The brown cow jumped over the log or something.
Yep. Tēnei au, te hōkai nei o toku topo wai, ko te hōkai nuku, ko te hōkai rangi, ko te hōkai a tō tūpuna tāne nui a rangi. I piki ai ki ngā rangi tūhaha ki te tihi o manono, i roko hina tūrā ko i o matua kore anake. I riri iho ai ko ngā kete o te wānanga, ko te kete tua uri, ko te kete tuatea, ko te kete aronui. Ka tiritiri a ka paupaua, kia papatu anuku, kia puta ko tātou, te ira tangata i te whaiao, ki te ao marama, whanno, haramai te tōki, haumi e, hui e, tāiki e. A tihei mauri ora. A tuatahi ake rā, me wehi atu ki ai hua whakahōneretia, te ariki nui, ngā waihono i te pō, tātu rā ki te kāhui ariki whānui tonu, pai marere ki ae o tira ki a rātu katoa. Ki ngā tini aitua kei runga ki tēnā ki tēnā o tātou, haere ngā mate haere atu rā, moe mai rā, oki atu ai, hoatu. Aputi hono tātai hono, rātou te hunga mate ki a rātou, aputi hono tātai hono, tātou te hunga ora ki a tātou. A nā ko nāno te hunga ora, ko tai mai nei, ka whakaeke nei, ki runga no i tēnei whenua tā ngai o Ngāti Pāwa, o te Kawarau Maki, o Ngāti Rongo ki Mahurangi, o Ngāti Whātua, nau mai, haere mai, whakatau mai rā. Whakatau mai rā i raro i te tuanui, o tēnei o ngā whare, e kia nei ko tukutuku, tēnā ingoa, ko tākoha tia e Ngāti Pāwa ki a mātau, hei tākoha, nōrera, nau mai, haere mai, whakatau mai rā. Mauria mai o koutou maunga, o koutou awa, o koutou katoa. Ki tēnei wānanga aronui o tātou. Kia aha, kia whai hua, kia whai rungoa, ki ngā take nui o te wā kei mua tonu i te aroaro. Nōrere tātou mā, nei ngā mihi, rarau, tēnā koutou, tēnā koutou katoa. Ka huri ngā mihi kia kōrua, Christine Richard, kōrua tahi, nau mai hara mai whakatau mai rā, e whakarangatira i tēnei noho tahi o tātou. Tātu rā, ki ngā kai kōrero o te pō, arā, kia koe Donna Rose Addis, nei te mihi kia koe, kei hea koe, where are you, Donna? Ngā mihi nui kia koe. Korua tahi kia koe te ahorangi, Robert Gourdie, e mihi ana kia koe. Me tō hoa, mai te primary school Blockhouse Bay, hoi anō, e mihi ana kia koutou. Hoi anō, nei te mihi ki tō tātou, maunukura tautoko tuarua rangahau kia koe, Professor Mark Orams, nei te mihi kia koe. Tātu rā, kia koe Brett, nei te mihi kia koe te ahorangi, te rangatira o tēnei pūmano o tātou, nei te mihi kia koe Professor Brett Cowan. Hoi anō ki ngā rangatira kei roto i te ruma, nei te mihi, tēnā koutou. Good evening, ladies and gentlemen, family and friends, and of course to our online audience, of which I believe number over 500. Welcome to Te Wānanga Aronui o Tāmaki Makaurau. Welcome to our kaupapa of the Auckland Medical Research Foundation and the celebration of 70 years. Nei te mihi. And of course, I'd like to acknowledge everyone who have swam through the hail and the rain, which is about to hit us very soon, to come and join us here in Tukutuku, here at the North Shore campus. Welcome once, twice, three times a lady. I'd like to also acknowledge special guests, Richard and Christine Taylor, for honouring us with your presence as well, and for actually solidifying this partnership as we move forward and for the next 70 years alongside ourselves as the Auckland University of Technology. Our name is Te Wānanga Aronui o Tāmaki Makaurau. And when we look at the word wānanga, two words spring up. The space, the wā, the time, and the ngana, which is when we pursue and we persist and we provide resilience to kaupapa or purpose or issues that are important to us here in 2025. Aro is to understand deeply, and nui is at a great deep level. So welcome to the Wānanga Aronui o Tāmaki Makaurau, where we come together and have robust discussions. And I'd like to welcome and thank also our guest speakers who have joined us. Donna, Robert, thank you for providing the insights to your areas of expertise, of which why we've all gathered here for this evening. Hoi no e te whānau, without any further ado, I better stop there, otherwise I'll have to invite Professor Mark Orams to sing my song for me. Hoi no, and we actually do want that. Hoi no, at this juncture whānau, welcome, tēnā koutou, tēnā koutou katoa at this juncture. Ka huri te tiripau, te rākau kōrero, ki tō tātou kai kawe kōrero mo te pō. I'd like to invite to the stage ki a koe Sue. E mihi ana. Ho mai anō te paki kia.
Ngā mihi nui, Dr. Smith and Auckland University of Technology for this wonderful evening here tonight in this beautiful building, tuku, and for hosting our 70th anniversary event. So kia ora koutou, ko Sue Brewster Takawingawa. For those of you that don't know me, my name is Sue Brewster and I am the Executive Director of Auckland Medical Research Foundation. And I am so excited to see so many of you here tonight, and as Dr. Smith said, through the hail and snow, you made your way, so we're extremely delighted, and also for those over 500 that are joining us online. So welcome one and all. So before I just say a little bit about our foundation, I just need to do a bit of housekeeping. So if you need the bathrooms, those are over to where you came in and down the corridor, and please feel free at any time to go to the bathroom. I assume those of you online know where your bathroom is, so I won't run through that for you. In the case of any unexpected emergency, please can we make our way in an orderly fashion out the front doors and just gather on the front grass area there and await further instruction. For those of you at home, you won't be involved in our emergency, so you can just stay where you are patiently. So this week is a very special one for us at Auckland Medical Research Foundation, as we're hosting our final events in our 70th year, an incredible year-long marking of the anniversary, and recognising awarding of over $100 million worth of medical research funding. So we're very fortunate to be joined by our 70th partners, and I would like to acknowledge and thank our hosts tonight, Auckland University of Technology, the University of Auckland, and Shaw & Partners, who were formerly JMI Wealth, for helping to make these events possible and for making this year such an extraordinary one. For those of you who aren't as familiar with AMRF as others, we are one of the largest independent funders of medical research in New Zealand across the spectrum of all diseases and disorders. So since 1955, we've been very fortunate to have such strong governance, some of which we have here tonight, is our President Richard Taylor and our Vice President Katie Noble. And we've also had a very strong medical committee. So this is a panel of medical experts and scientists and researchers, and their job is to put a really robust criteria around evaluating all of the applications that come into us. So I'd love to be able to tell you that we can fund all of those applications, but sadly we can only fulfill about under 20% of those that are eligible for funding. However, the great thing is that all of our donors and the generous donation spirit means that we can fund up to about $4 to $4.5 million annually. And even in these times when the research pools are diminishing from other sources, our board has committed to a minimum of $4.5 million being awarded every single year. So I thank all our donors who are here tonight, as we couldn't do this without your support. We know one of the things our donors really love about us is that all of our operating expenses are covered by an external benefactor. So that means every dollar of every donation goes straight into our purpose, which is funding world-class medical research, which is why you're all here tonight. So I hope that gives everyone a brief snippet of our foundation, and now I'm just going to give you a quick rundown of tonight. So our first presenter is Professor Donna Rose Addis, who I'll introduce very shortly. Donna Rose will share her latest research, and that will take about 40 to 45 minutes. Then we will have time for those really important questions you'll all have burning after her session. Then we'll take a break for a light supper, and we will resume again about 7:30 p.m, where we'll welcome Professor Robert Gourdie to the stage, and again we'll have time for question and answers at the end of his presentation, wrapping up about 8:30 tonight. So I would just like to start the introductions of our guest speakers by thanking the Ted and Molly Carr Medical Travel Fund for helping to bring these two exceptional professors back to New Zealand for our 70th anniversary. And we have one of the trustees here tonight, Gourdie. I'm not sure where Ron is, he's here somewhere. But thank you very much for making this possible. My first introduction is of Professor Donna Rose Addis. Donna Rose grew up in South Auckland and is the first Samoan neuroscientist, specialising in neuroimaging, and has been living and working in Canada since 2018. In 2016, Donna Rose was made the youngest ever Fellow of the Royal Society of New Zealand. She has been recognised for her pioneering work in the use of functional brain imaging to study how the brain stores and retrieves memories in healthy people and those suffering from neurological diseases. Donna Rose's work focuses on understanding the relationship between memory and imagination, the ways in which future imagination differs with age, mood, and mood disorders such as depression and memory loss as a result of amnesia and ageing. But the very best person to tell you about her research is, of course, Professor Donna Rose Addis, and I would ask us all, please, to put our hands together and give her a very warm welcome.
All right. Talofa lava. Good evening, everybody. It's an honour to be here this evening, and thank you so much to AMRF for having us, both of us speakers here this evening. So I'm really excited to be able to share some of my research with you this evening on the aging brain and how healthy aging as well as dementia affect our ability to remember the past and imagine the future. So something that we do as neuroimagers is that we put people into an MRI scanner, and while they're in there, we ask them to do certain kinds of cognitive tasks. So we might be, in this case, asking them to complete sentences. And so then when we do our analysis of the brain activity, we're looking to see what's really active when people are doing this particular cognitive task. But something that was a very fascinating finding that emerged in the literature around 2000 was that actually the brain is highly active when it is resting. So the main point there is that the brain is never truly at rest. And the brain network that emerged while people are in this kind of resting state is something that we're going to explore further tonight. So one of my colleagues asked people while they were lying in the scanner to indicate what they were thinking about when they were in this kind of resting sort of state. And so some of you might recognize this as things that you do when you're kind of not engaged in some other kind of task. Some people said they had a blank mind. Some people were doing things such as counting. Some people were, maybe focusing on something that's in front of them. But many people said that they were thinking about their past and their future. And indeed, researchers that have done thought sampling research, where they basically send people a text message and say, what are you thinking about right now? It turns out that we spend half of our waking time mind wandering, or in this kind of resting state. But actually, our brains are doing a lot of work. And half of that mind wandering, as I mentioned, is on the past and the future. And this really underpins a major change that we've seen in the memory research landscape over the past 20 years. So previously, people really focused on remembering past experiences and understanding the brain correlates of being able to do that. Whereas in the last 20 years, we've seen this transformation of memory research to focus on how it enables us to imagine the future and imagine ourselves in it. And so that'll be what I'll be talking about tonight. So firstly, I'll be outlining why it is that we imagine the future. Then secondly, how the brain allows us to imagine in such rich detail. And then thirdly, how aging affects the imagining brain. Okay, so first, why is it that we imagine the future? So if we spend half of our waking lives doing this kind of thing, it must be some sort of adaptive function. There's many forms of how we can think about the future. So we can have visions of a future self or someone that we would like to become. We can hold goals and plan the steps to attaining those goals. We might have to-do lists. But the type of future thinking that I'm most interested in is mental simulations of the future. So our ability to imagine experiences that have not yet occurred. So, for instance, for me, all day it's been thinking about being up here and giving this talk this evening. And the characteristics of these mental simulations are that they can often be very dynamic and video-like. They usually contain information about the places and the people that you expect to be there, sequences of actions and consequences, but they're also highly flexible. So the amazing thing about trying things out in our mind is that we can redo it until we get it right. So future imagination then enhances our future success. It enables us to troubleshoot and problem solve in advance, to allow us to adapt our behaviors, assists us in planning and making good decisions, and increases our coping and reduces our worrying about upcoming events. But interestingly, research has shown that not all future imaginations are the same in terms of their capacity to be useful. So there is a distinction that's been made in the science on future thinking between what is called a process simulation. So this is mentally simulating or playing out all the steps that you need to achieve to reach a goal. So for myself, going to the University of Auckland and getting my bachelor's degree, I had to think through what all those steps were going to be so that hopefully at the end I would be successful in getting my degree. So these are associated with realistic expectations and also details about what steps we have to take and what might actually happen along the way. Another type of simulation that people have is known as an outcome visualization, simulation. This is also known as creative visualization, is what it used to be called in the 80s. Now it's called manifesting. And this is where you actively visualize attaining the desired outcome and experiencing that positive emotion. So it's almost like you experience that in advance, and it's often associated with very idealistic expectations. And so one of the things here is that it can, you feel like you've already achieved the goal in a sense by having that emotional, the positive aspects of achieving the goal, or you might set yourself up for failure in some ways. And so there's been now a lot of research looking at different kinds of situations to see how these process or outcome simulations help people in their day-to-day lives from a range of behavioral scientists. And so some of this, looking at process simulation, is a lot of very convincing evidence around exam performance. In one study, they actually had to stop the study because the students who were not doing the process simulation actually started to perform much more poorly than people who were doing nothing. So it can lead to more study behaviors, less anxiety, and better grades. Outcome simulations have been shown to actually impact people's recovery from hip surgery. So people are less prepared for their setbacks, put less effort into rehab, and end up having poorer outcomes. There's also work showing that actually maybe having a balance of the two is an ideal situation. So in studies looking at exercise, if they have individuals imagine both a challenging process but attaining a positive outcome, people have better adherence to their exercise programs. So that's all well and good, but how is it that our brains actually allow us to do this? So that's where my research has focused for the last 20 years. But the story starts back in the 1950s with an individual Henry Mollison, or also known as patient HM, who was unable to recall the details of any past experiences following surgery for epilepsy. And so he became one of the most famous patients with amnesia. And so, I don't think I have a pointer here, do I? No. So anyway, HM, as you can see on the slides there, had bilateral removal of his hippocampus. And so this was what really clued scientists on to the fact that the hippocampus, the structure that sits in the inner part of our temporal lobes, is actually the hub in the brain for memory. And so in around the late 2000s, he sadly passed away, but his brain was autopsied and very finely sliced so that we could get a very fine understanding of how it was that his hippocampus was damaged. And as you can actually see here, on some of these slices, you can literally see where the scalpel cut his hippocampus. So there's kind of some very straight-looking lines in there. Another individual that's helped us a lot is Kent Cochrane, or patient KC, who's actually from Toronto. One of the reasons I think that Toronto has become such a hub for memory research is that we actually have a number of amnesic individuals who donate a lot of time to doing research. And Kent had bilateral hippocampal damage after a motorcycle accident. And the interesting thing with Kent was that there were hints about a link to future thinking from some of the work that was done with him. And so this is an interview from 1985 where the interviewer, who, for those of you who know memory science, this was Endel Tolving, so one of the fantastic scientists in memory research. And as you can see in this transcript here, he says to Kent, "What will you be doing tomorrow?" And Kent says, "I don't know." Do you remember the question about what I'll be doing tomorrow? Yes. How would you describe your state of mind when you try to think about it? Blank, I guess. And so the thing here, he described it as how it was for when he tried to remember the past as well. So in both cases, his mind was blank. And that really gave us some clues to the fact that maybe memory is really linked to this ability to imagine the future. And so then in the mid-2000s, we decided to actually have a look and see whether there was brain imaging evidence of this link between past and future. And so we would put people in the scanner, into the MRI scanner, and instructed them at some points during the scan to remember some past experience to do with, we would give them a cue word to just kind of get their mind going to think about something. So here I might be remembering when I went and picked up my dog Jackie for the first time. And then sometimes we show people a cue and we ask them to think about the future. And so we might imagine taking our niece out to the botanical gardens or something like that. And so here, what we're getting people to do is really engage in this mental simulation while they're in the scanner and look at their brain activity. And the thing that was so striking to us was that when we looked at the neural correlates, they were nearly the same. So the same brain network that activates when people remember their past is activated robustly when they imagine their future. And something that struck us at this time, we were trying to really kind of come up with a theory about why we might see such overlapping activity. Well, we'd known for about a decade or so at that time that memory for past experiences is highly constructive. And so what we mean by that is that even though memories of experiences or events might play out like videos in our mind, they're actually stored as individual details across the brain. So in the different parts of the brain that process that information in the first place. So our visual details are stored in our visual cortex, the auditory details in auditory cortex, and so forth. And then what our brains have to do when we remember is to locate all the details that belong to a particular memory and integrate those. So it activates them and integrates them so we experience a very seamless memory. This does have side effects or downsides. So one is that sometimes we have memory errors. So we might bring the wrong detail into a memory and remember that someone was at a particular dinner party when they weren't there at all. But the benefit is that it actually means that we can use these details, we can easily extract them from different memories and recombine them to construct novel simulations of events that we have never experienced before. And so in this way, we can think of memory as providing the fodder for imagination. So one of the brain regions that's most critical to this is the hippocampus, so the one that was damaged in the patients with amnesia. So interestingly, in our fMRI studies, we've actually found that the hippocampus is more active when people are trying to imagine the future than when they're remembering. So this was quite a transformation in how we thought about this part of the brain that for about 4 decades we had really thought of as a memory structure in the brain. But now we know that it's also really important for imagination. And I have spent many years trying to understand why that is. And one of the things that we think is that it's actually about recombining the details to create an imaginary event. So our hippocampus is working hard to put together these details that have never been associated before into something that is coherent and makes sense to us. So we've done a lot of studies that have shown that imagined events that have more detail in them have more hippocampal activity. So this tells us then that the activation of the hippocampus is scaling with how vivid an imagined event is. It's also highly activated when we imagine something very specific. So if I were to think about, going through the same routine that I go through every morning, and it's kind of, something that's just so routine for me and doesn't have a lot of detail necessarily, then that's not going to have as much hippocampal activity as if I imagine something very specific, but also something that's very novel. And so novelty is really important here as well. So in this study, when we had people imagine an event for the first time, we saw a lot of activity in the hippocampus, but if they repeatedly imagine that event, over time that activity would decrease. So when we're first putting something together, we see a lot of activity. Okay, so in the last part of my talk this evening, I'm going to really be focusing on aging and the imagining brain. So as we get older, our brains begin to show evidence of atrophy. And so this is something that's just part of healthy aging. And so in this study here, what we see are the brain regions that are showing a percentage of volume loss over 2 years in people aged over 65. And so what we're seeing here is that the very light blue regions are the ones that are showing more of a percentage loss in volume over those 2 years. So here we're looking at MRI scans that have been collected from these individuals on an annual basis to track what parts of the brain are actually losing tissue. And so interestingly, part of what we see here are a lot of volume loss in regions that are actually part of that imagination network. If I had a pointer, I would be able to show you some of these regions, but that's going to be a little bit difficult to show you. But on the left-hand side, what we can see are regions on the lateral. I don't think there is. Oh, yep, got it. All right, thank you. That's great. All right, I'm going to stand around here. So what we can see here, this is the lateral side of the brain, so looking the outside in. And these MRI scans look a little unusual to people when they see them, but what it is what we call an inflated MRI scan. So they've just blown out the MRI scan so that you can actually see what's happening in all the parts of the brain, rather than it kind of being all folded in on itself. And so what we're seeing here is activity when people are imagining in the lateral temporal cortex, the lateral parietal cortex, and then this is on the medial surface of the brain. And so we see activity in the medial prefrontal cortex, so just behind the eyes, and then here in the posterior medial cortex. And just tucked in here is the hippocampus. And so that's that brain region that's highly important for being able to imagine. And what's really interesting here is that many of those regions that are showing in the light blue are a number of the regions that we see as being really important in imagination. So they're the ones that are showing a decrease in the volume of those regions, so meaning that there's been some cell loss. And so here's a kind of another result here where they're zooming in on these different parts of the brain to actually quantify how much volume is being lost over the course of a year. And so what we see in healthy individuals is that, sure, there's definitely some degree of loss, around 0.5% a year, in both the frontal regions as well as in the temporal regions, which include the hippocampus. And then this is what it looks like in Alzheimer's disease. So I put this up because I think it's really important to emphasize that in healthy aging, yes, we might be losing some brain volume, but it's certainly not the same as what's happening in people that have dementia, where that's just much more accelerated. But what is interesting as well is that actually even in healthy individuals, the older you get, the greater the loss of volume in the hippocampus. So if you're aged here at 80, you're losing around 4% per year. But when you're around 60, you're maybe not losing too much at all. So that kind of indicated to us that it was really important to be able to look and see what was happening in healthy aging when people are trying to imagine the future. And particularly because we know that also memory is affected. So we had, and this is the very first study that anyone had done looking at this. So we had 16 younger adults aged 18 to 30 and 16 older adults aged 65 to 80, all very healthy individuals. They would come into the lab and we would have them do a past-future task. So again, we would show them a cue word to get their mind going, and we would have them recall or imagine as much detail as they possibly could for 3 minutes about the event that they were thinking of. And then myself and many students over the years have done the very intensive task of taking every transcript and segmenting that into individual details or pieces of information that people are generating, so usually a couple of words at a time, and then scoring those as either episodic details, and so that's the details that are very specific to the event itself. So information like the time, the place, what was happening, and any kinds of experiences the person was saying that they had at the time. So this could be perceptions, things they're seeing around them, their emotions, or their thoughts at the time. And we separate these from non-episodic details. So these are facts or background information, their current thoughts that they're having at the time of doing the task. So if they tell us it's a difficult task or that they're really enjoying the interview, and then any repetitions and things like that people generate. So here's an example from a younger adult who is thinking of a future event in response to the word oven. And so they say, I imagine baking my first loaf of bread. It'll be the Friday before Yom Kippur. I get the recipe from an old cookbook. The room is hot even though we have the windows open because the oven is on in the middle of summer. The bright kitchen light is off and we light a candle. The BBC is on in the living room. And so you can see from this quite evocative description of this imagined event that this person's generating, something that they've never experienced before. And here's an example from an older adult, a memory that they're retrieving in response to the word toy. So they say, this reminds me of those toys our grandchildren have. I think they're spoiled. Our son, the teacher, doesn't have a lot of money, and his wife just can't say no to the kids. I generally give my son money for specific things. Like he had a problem with his knee, and so to help with the doctor's bill, I gave him some money, and I wrote on the check, don't spend this on toys. And so you can see in there, there's the kind of background information in green that's not, really related to the one specific event that they then tell us about. So they kind of get to this point where they're then imagining, in this case, remembering the specific moment where they wrote the check and wrote that on the check. And so this is kind of what was evident then in our results was that, and just to orient you here on the slide, we have the number of details on the side here, and then we have the episodic details, so the event kind of information, and then the other kind of non-episodic information. And so what we see in the older adults is that they show a decrease in the number of episodic details that they're remembering when they're remembering past events, but they show an increase in the non-episodic information. So they're recalling more of this contextual information than younger adults. And what we found was a striking similarity again for future events. So again, we're seeing this kind of overlap between the two processes. So for future events, older adults are generating or imagining less of this kind of vivid detail, but more of this kind of contextual information. And I think that's really important to note because it's not all about decreases. So this is actually telling us something about what one gains with age, and that's really important. The idea that as you get older, you have a broader context and more wisdom and repeated experiences that you've learned over a lifetime that you can start to contextualize information better. Looking, though, for our kind of research, we're very interested then in the correlation between the past and the future. And so what you can see on this graph here is a correlation between the number of past details that people are generating. So each dot is a person. So people who tend to generate fewer details for the past are also the ones that are generating fewer details for the future. And so what that tells us is that being able to access details from your past is really important to being able to imagine a detailed future. And so that really speaks to our theory that we're really taking details from the past and recombining them to imagine. So turning to neuroimaging work that I did with Rhys Roberts, who's at the University of Auckland. Here we had younger and older adults in the scanner, and we were asking them to do our task where they're remembering and imagining, and we compared this to a sentence task, so where people had to complete sentences. And so what you're looking at here is activation in that imagination network. And by and large, younger and older adults activate the same network. So we see robust activity in both young and older adults. And so what you're seeing in these graphs here is the amount of brain activity when people are remembering or imagining in these warm colors, as opposed to when they're doing the sentence completion task. And so you can see that in younger adults, they're really showing this increase in activity in this particular brain region. Older adults are also showing this difference. It might not be as big a difference, but it's still there. So it tells us that they're engaging these regions when they're imagining. But there were some important differences. So what we see is that there were some regions where we see a decrease in brain activity, and one of these is the hippocampus. So as you can see here, younger adults are really activating that region for the past and future tasks. Older adults are not showing that same activity, so there's no differentiation between the lines for the different tasks. And there were other regions that showed age-related increases. So where older adults were actually showing more activity, and this happens to be in the lateral temporal cortex. And this is a region that we know is actually underpins conceptual information. So our understanding of general knowledge and how things work in the world. And so we think this is related to that kind of being able to contextualize information and put it in a broader context, understand the broader meaning of different things. And so we also, while people were in the scanner, they had to rate how detailed each event that they remembered or they imagined was. And so we could do analyses looking at those detail ratings to see if there were particular parts of the brain that would scale its activity or modulate its activity with the detail ratings. And in younger adults, it happened to be the hippocampus. And so that was something that reflected, findings that we'd seen before. But interestingly, in older adults, it was this brain region in the lateral temporal cortex. So really reflecting the bringing in of all this kind of conceptual information into those imaginings. So more recently, we've been looking at individuals who are at risk of cognitive decline. So in this case, this was healthy individuals in this, or a community sample of individuals who didn't have a diagnosis of cognitive decline, but are potentially at risk of developing it. And how we looked at that was that they did a dementia screening test. It was actually the MOCA, which some of you might have heard of because it was the one that Donald Trump did a few years ago and was all like, oh, I'm great because I did well on this cognitive test. And so that's something that we use to screen people to see if they're showing any signs of dementia. And so what we can see on this plot here is that we have the score and the number of participants in our study, and we have this line at 26. That sort of gives us an indication of sort of where people are at. And it's somewhat arbitrary. We just kind of divided our sample there so that we had half of the people above that line, half below, in an effort to see whether there was any indications of anything changing in the brain. And so here we used a type of imaging that really allows us to separate out and measure the volume of the different subfields within the hippocampus. So what we've just been looking at so far is just the hippocampus as a whole, but now imaging, MRI imaging has gotten to a point where we can really go in there and measure each individual subfield and look at the different kinds of neurons that are in there and the volume of those regions. And so what we found in these individuals is that the ones that were below the dashed line, so the ones that we think could potentially be at risk of developing later cognitive decline, they actually did have a decrease in the volume of one particular region in the hippocampus, the anterolateral entorhinal cortex. So that led us to then think, well, shall we have a look at people's ability here to remember and imagine, and is that related, or do we see a difference in people that have a volume decrease in this particular brain region? Oops. Okay, and so what we found there, we did the same task where we had people come in and well, actually this was during COVID, so we actually did it all over the phone. So we interviewed people over the phone, and they did our memory and imagination task, and we found a very similar pattern to what I showed you before, was that people that are at risk of potentially developing cognitive decline showed a reduction in the episodic details, making up their remembered events and their imagined events. But they didn't show any difference from their aged matched peers in terms of that non-episodic detail, so all that kind of contextual information. And again, we see that same correlation where people who are not as good at generating many details when they remember are also the ones who are producing lower detail when they imagine. And then in other work, we've looked at individuals who do actually have Alzheimer's disease, and of course there we see significant damage to the hippocampus. So as you can see here, but also the surrounding cortices, including that lateral temporal cortex that I was telling you about earlier. So the one that in healthy older adults, they're actually engaging that region more when they're doing these tasks. So what would happen then in individuals where this brain region is impacted? And so here what we found was that both episodic and non-episodic details are impaired. So we're seeing then for the episodic, is that not working now? I don't think it is. Okay. So the episodic details, we're seeing a decrease in people with dementia, but we're seeing that same decrease for non-episodic details as well. And importantly, again, we're seeing the same kind of reduction for both past and future events. So again, this is really showing us that that's an important relationship. But it doesn't always play out this way. So a very interesting study that we did a few years ago with colleagues in Australia was looking at semantic dementia. And so these are individuals that actually have volume loss in the very anterior part of the temporal lobe, and particularly on that lateral cortex. But they don't, it's a very kind of specific area of damage. So it's in individuals with semantic dementia, they're showing decreases in their kind of conceptual information, their memory of facts and names and words. And what we found there was that this only affected future thinking. And so you can see here, we have semantic dementia individuals in the middle and Alzheimer's disease individuals in the white bars. And so the two blue bars, comparing semantic dementia patients to control participants, there's no difference in their ability to remember the past. But when you look at the future events, we now see semantic dementia patients performing at the same level as people with Alzheimer's disease. And so this was a very interesting finding for us. We really, really had to think about what that meant. And this was something that led to us hypothesizing about the role of semantic memory and schema when we're trying to imagine something novel. So the idea there being that when you are trying to imagine something from scratch and you don't have anything to base it on, if it's something highly novel, you need to have some kind of semantic information about how the world works. So if I'm going to imagine going into a restaurant, I need to understand that, I will be asked to wait until I'm seated, I'll then order, I'll then, have dinner before I have dessert. And so that gives me a framework within which to imagine. The interesting thing here was that, without that kind of framework, people's ability to imagine things that are highly novel is very impacted. The other interesting thing was that when they did imagine, what these individuals were doing was what we call recasting. So they were taking a memory from the past and just imagining that happening again in the future, with nothing additional added. And so that's now led us to a new direction where we're starting to look at this process of recasting to see actually how common it is. Because we think actually, a lot of our experiments have really pushed people to imagine things that are highly novel, putting them in getting them to imagine unusual things that might never happen to them. But what are people doing on a day-to-day basis? And so in a recent study that we just did in young and older adults, we found that by and large, that's what people do. They recast. So 83% of the time, that's what people are doing. So we're now following that up with neuroimaging to kind of see what the neural correlates are of that process. So in some other new directions that we're taking in the lab at the moment, one of these is looking at approximal future thinking. And so this is a new kind of concept, if you like, where what we're looking at is how our brains play out what actually is going to happen, or what we think might happen next in the moment. So this is a very interesting phenomenon because not only are we perceiving what's around us, but we're sort of overlaying this imagining of what could potentially happen next. And often this is elicited in very negative or high threat situations. So for instance, walking downstairs or walking along a dark street at night. And so we're really interested in seeing how that looks in terms of the brain regions that are involved, and whether regions that are really highly engaged during emotional processing, like the amygdala, come into play. And then in another direction is that we've just started a new study looking at after death and intergenerational future thinking. So this, we think, is really important in terms of people's well-being, and thinking about, how we're kind of leaving things for other generations, but also this was really inspired by my grandmother, Rose, as you can see here, on her 100th birthday. And we were very interested to see, or I was very interested, when I would be talking to her about how much she would think about what she was going to do after she died. So she would have these very vivid imaginings of meeting her siblings who had passed on before her. And this is a form of imagination that, people really in the literature haven't looked at all, but is likely very highly prevalent and very, related to people's well-being, their psychological well-being. And so we've started doing work on this, where we're looking at how it's related to different kinds of belief systems around time. And so some individuals, believe in reincarnation or in spiritual embodiment and persisting on over time, where others do not. And we've found that this actually relates to people's time horizons. So how far they see the future extending in front of them. So that if they believe in reincarnation or spiritual embodiment, they have a much more extensive sense of the future, and that is highly related to their well-being. So that's just a brand new kind of area that we're getting into. And following up on that, we're actually having people imagine events, related to themselves after death, but also to their family members and their communities. And so we think that's a really new, interesting direction to see how it is that we're able to imagine what might be, coming for generations ahead of us. Very important when it comes to things like environmental concerns or things like that. So how we can use future thinking to actually help people engage with some of the problems now that might not have impacts for us today, but may have impacts for individuals in the generations to come. Okay, so just to conclude then, imagining the future is a highly adaptive capacity. So it helps us to plan not only for our futures, but also to enhance our success and maybe the success of future generations. Imagining details and steps is very important in this actually having good outcomes for us. The past and the future are inherently linked. So both abilities are dependent on the brain's default mode network, so that imagination network, and the hippocampus. And the hippocampus is particularly important for imagination, as it can help us to recombine details into novel combinations and to experience things that we have never actually experienced in our lives. The aging brain imagines the future differently. So there are these age-related changes in key brain regions, but and we see changes in the types of details that people are imagining. But importantly, there's a change in the balance of information that people are coming up with. So it's not that it's all about the loss of memory and the loss of future imagining, but that we imagine different things. And in our newer work, we're showing that this capacity to imagine future events may extend beyond one's own lifetime and may have impacts for one's psychological well-being as age advances. So that's it from me. Thank you so much to my collaborators and my trainees, my sources of funding, also the Ted and Molly Carr Medical Travel Fund, who brought us here, and to AMRF for having us here tonight. I really appreciate the opportunity. Thank you so much.
Thank you very much, Professor Donna Rose Addis. That was incredible, and I am sure we all learned a lot tonight. I could see all your imaginations running wild as we were speaking. Light bulbs were going on. So now is some time for question and answers with Donna Rose. Please make sure we've got 2 roving mics. Please make sure when you ask your question, ask it directly into the mic so that our people online can hear. So who has that burning question? Hannah's going to come your way with the microphone.
I wondered about fiction readers and whether any research has been done on those in terms of fiction always being about imagination as opposed to non-fiction books.
Yeah, no, that's a really, really great question, and there is work that's been done on that. Interestingly, that same imagination network is really engaged when people are imagining fictional stories, and also when they're thinking about experiences of other people, so even people that we know, right? So like if you're taking the perspective of somebody else, so something called theory of mind, you see that same brain network activated. And interestingly, there's been some recent work that's been showing that individuals who read fiction actually have better theory of mind. And so the idea there is that if you're, really engaging that network as you read, and you're also, taking different perspectives, you're almost practicing those kind of social capabilities through reading. So it's a lot of very interesting work about fiction, and that the role of that network in allowing that to, kind of to project us not only, out of the present into our own lives, but into the lives of other people and into imaginary worlds.
Thank you, that was wonderful. I've got a question that relates to a developmental thing with imagination.
Yeah.
I remember as new migrants, our son went to one intermediate, he was at year 9, secondary school, and then, which was high decile, and then he went to another one that was a lower decile a year later. And his comment was that he felt that the people in lower decile schools weren't necessarily able to see their futures in the same way that he felt that Onslow, which is where he started off, was able. Now, the differences that you've been talking about have been between diseased and non-diseased older brains. I was just wondering across the lifetime what other factors might affect people's capacity to imagine the future.
That's a really great question. And actually something I think that I experienced in my own lifetime, having gone to a very low decile school myself, Aorere College. And I think, it actually, my research speaks to this in the sense that it's very hard to imagine things that you have no experience of. And so that idea that you have to have memory or, experiences to draw upon to imagine things and to see yourself in the future really, I think speaks to what you're talking about there. So I think there wouldn't necessarily be differences in the brain or the imagination network, but just that what you're able to imagine is really constrained by your own experience. And so certainly in my own career, it was always people around me that gave me a model of who I thought I could be, right? So I actually went to university to become a history teacher because I had a really fantastic history teacher at high school. And then I met this amazing cognitive neuroscientist at Auckland University, and I was like, okay, I want to be her. And so then, now I still work with her, but so it's kind of sometimes you really, there's huge value in opening, the world up to children. So I think in terms of though the brain differences, there's no difference in terms of like what's actually happening in the brain. But actually, you also brought up the idea of developmental differences, and I think that's interesting because children, of course, we know are very have an amazing capacity to engage in kind of imaginative worlds and an imaginative play, and one of the things there is that they sort of don't have the constraints of, firstly, experience. So there's something to be said about, you know, that once we sort of experience certain things and our world and our views kind of narrow, we're less able or less flexible in terms of what we're willing to imagine, because we're like, well, that just wouldn't happen, so I'm not even going to think about that. So I think that's one change that we see developmentally. Another is that, you know, our executive functions, or our frontal lobes, develop, right? So people know that, you know, it takes probably till in your early 20s for your frontal lobes to really fully develop, but that's what really underpins our executive functions, or our abilities to kind of make sense and reason and plan. And so it's kind of like kids are imagining without those without their frontal lobes on. And that's a little bit like what we see when people are dreaming as well. So when you're dreaming, you're recombining bits and pieces of information, or with knowledge that you know. So, you know, having dreams where people are not where they should be, or, you know, all sorts of weird things are kind of playing out. And that's because your frontal lobes are not really directing or guiding what you're imagining. You're just imagining things with the information that happens to be highly active, you know, because maybe you thought about it yesterday or you experienced something. So there's some really interesting work going on looking at how, you know, if people experience certain pieces of information during the day, are they then showing evidence of that in their dreams? And so actually, yeah, so it's kind of a very interesting field. Very hard to do that kind of research, though.
Can I ask you a question?
Yes.
You talked about the mass reduction in the brain.
Yes.
Do you actually measure that from people's brain tissues after they've died, or were you just estimating that?
So those studies are using MRI scans, and so they're like actually measuring the size of the grey matter that we're seeing on the MRI scans, but then those are validated against, you know, studies where they've actually done autopsy results. And so, and often too, in these cases where we have people with amnesia, that's something, you know, very, usually very important that they do after they die, is to really, you know, they've been so intensely studied while they've been alive, we then, and we, you know, have MRI scans on them, but then to really get a good sense of exactly what had happened to them anatomically in their brain, in terms of the pathology, we do a lot of deep autopsy types of results afterwards. Yeah.
Yep.
Yep.
Hi. I just was wondering if you had anyone in your testing groups who actually didn't have an imagination, and if so, did they carry on with the testing? Because
Sorry, could you
sorry,
speak a bit louder?
nervous talking. Sorry. Did you have anyone in your testing groups that didn't actually have an imagination?
Oh.
And if so, did you carry on with their testing? Because I found out when I was 50 that everyone else had an imagination.
Right.
And I didn't.
So do you mean in terms of like a visual imagination? Yeah, so that is an interesting area of study, and we actually have somebody here who this evening who does work in this area too. So it's becoming a very very kind of studied area. I would say in that sense, I have never, you know, in all the years that I've done this research, I've never had anybody not be able to do my tasks. And that's because you don't have to have a visual imagination to do it, right? So you can be imagining in all sorts of ways, with all sorts of senses, but also I think a lot of what we're seeing in people is actually what I would probably call verbal reasoning. So they're actually thinking through and kind of verbally talking about, well, especially because we ask them to do this verbally as well and to describe to us, but even when we look at the brain activity, it seems to be more dominant or stronger on the left side of the brain, which in most of our participants would be their language side of their brain. So I think there's definitely a big verbal component to being able to do this. And when you think about, you know, if you're planning what you're going to do, a lot of what you do is, or at least for some people, is to talk to themselves, right? So I think other people may not do that and may focus more on the visual side of it. So yeah, so I think there's many ways to kind of achieve the goal of being able to imagine the future. Yeah.
So we've got time for one more question, which is over here, and then, sorry, we do have to break for supper and we have to keep on time just for the online people as well. So we've got one last question coming up.
You said the hippocampus, they lose, or older adults lose a certain percentage. If they engage or continue to engage in studying something which unrelated to their existing knowledge, will they still lose a certain percentage in the older adults, the hippocampus?
Oh, that's an interesting question. Yeah, I don't think anybody's actually done research on that, but that could be something that that would be a very interesting project to do. Yeah.
Oh, yeah.
Yeah. I mean, I think any time that you're sort of trying to engage with new information and to just kind of keep your brain, you know, active and engaged is in whichever ways you wish to do that. And so that might be like somebody was saying, fiction, or, you know, imagining other kinds of things. But I don't think there's been any research that's actually looked to see whether that has any impact on the volume loss that we see in aging. So, yeah, you can maybe come and help me run a study there.
Yeah, I will. If you learn a new language or something at the age of 70s and 80s, then you know you're actually working your brain.
That's right.
So my belief, the more you work your brain, the more active it is. And you'll not lose with age and you'll still remember. Because people say, I'm grown old, so I've forgotten. That will not happen. So I wondered whether the brain remains young, even though you're an older adult.
Great, thank you.
Wonderful. What an amazing session. Thank you very much, Professor Donna Rose Addis. Can we all please put our hands together?
Thank you.
So, Donna Rose, of course, will be joining us for supper, but there'll probably be a queue to talk to her. So please help yourself, tea, coffee, there's a savoury and a sweet, and then we'll try and be back and seated by 7:30 at the latest, please, if possible. Thank you very much. ora, is it on? Hello, hello. Kia ora, everybody. Could I please ask if you could make your ways to the seats? Please take your tea and coffee and snacks with you. We don't have any popcorn, so bring your savouries and your sweets and make your way back to your seats, please, so we can kick off. Hello. We're actually going to kick off the second part of the proceedings now. Some people are just still making their ways back, so please just do so in a safe manner. So after that incredible address by Professor Donna Rose Addis, I am delighted to introduce our second speaker for this evening, who is Professor Robert Gourdie, a New Zealand-educated scientist and internationally acclaimed cell biologist specialising in cardiovascular and biotech innovations. I was just going to say, can everyone hear? Good. Robert has worked in the United States since the late 1980s, and his research spans from fundamental cell biology to therapies moving towards the clinic. His lab has led promising treatments for wound healing, heart protection, and cancer, and Robert and his team have pioneered technology turning milk exozymes into an almost ideal oral drug delivery system. Robert is now studying his own alpha-CT1 peptide for heart attack protection and as a radiation mitigating drug for cancer patients. Robert completed his undergraduate and graduate studies in Aotearoa, New Zealand, before doing his postdoctoral research at University College London.
He is the Hayward Fralin Professor at Virginia Tech and Director of the Centre for Vascular and Heart Research at the Fralin Biomedical Research Institute at Virginia Tech. He also co-founded in his spare time Zequel Bio Inc. and is the founder of the Tiny Cargo Company. Please join me in welcoming Robert so he can tell you about his fascinating research and career. Can everybody hear?
No.
Okay, it's working now. Let's put it a little bit higher up on my lapel here. Okay, can you hear me now? Yeah. All right. Well, again, thank you for that kind introduction, Sue, and also thank you to the AM. I can't see. Oh, okay. I want to stand off my slides because I'm going to point at them. So if you'll bear with me, I'll get up here then. All right. So thanks again to Sue for the wonderful introduction. Thanks to the AMRF for the invitation down here to speak. And so, let's move it again. I'm sorry that I should have got this sorted out earlier. Okay, so what you can we go back a slide? All right. So I live in Virginia and in the Appalachian Mountains. This sort of resembles what it looks like off the back of our deck in the evenings. It's a very pretty place. All right, so just a little bit about me. As Sue said, I'm New Zealand educated. I'm not actually New Zealand born. I was born in Zambia in Africa. And my parents arrived here in 1965 and I can distinctly remember standing on Princess Wharf as a 5-year-old. It was actually my 5th birthday on the day that we arrived. And so, of course, we were refugees basically from a place of conflict. And I guess they had a word for them back in the day. They were called 5-pound poms. We weren't actually Poms, we were from Africa, but nonetheless the appellation applied. Now, I grew up, as Dr. Smith referenced in his fine talk, in West Auckland, attended Blockhouse Bay Primary, went to Green Bay High School. In fact, one of my dear friends from Blockhouse Bay Primary, Brad McCullough, is right here. I met him when he was 5 years old, so basically I was off the boat, literally. Now, as it would happen, during my teenage years, I actually worked on dairy farms to make a little bit of extra money, which is kind of ironic given where I ended up. And so this was a familiar scene to me. In fact, it still makes me glum to this day if I hear the sound of a milking machine on the television or something, because I think, oh my gosh, it's 4 o'clock in the morning. I've got to get up. Yes, well, warm something, but we won't go into details. So I went to the University of Auckland to do an undergraduate degree and then proceeded on to do a master's degree. And my academic aspirations really didn't ignite until I was in my master's year. And this gentleman here, Professor Stanley Bullivant, was one of the individuals. He was a professor of cell and molecular biology at the University of Auckland, and he really got me interested in intercellular junctions, which is really where I've spent most of my academic life. I came from a family of modest means, and so at the end of my master's, I knew that I wanted to do a doctoral degree, a PhD, a research. And there really wasn't any money to do it, to stay in Auckland, but I did get a scholarship from the Ministry of Agriculture and Fisheries and ended up down at Lincoln College, which was then part of the University of Canterbury. And in fact, I wasn't actually at the college. I was at an organisation called the Wool Research Organisation of New Zealand, and my PhD was on the biophysical properties of wool fibres, believe it or not, which, you know, I quite enjoyed. It was a pretty fascinating area, but, you know, there's limitations to the number of times you can stretch a wool fibre and gain information out of it. And eventually I decided that I wanted to move on. Now, I actually ended up in London doing a postdoc, and I'll come back to this in a minute because Stan Bullivant, my professor at the University of Auckland, was important in this. But where I'm at now is a place called Virginia Tech. And Virginia Tech in many ways has similarities to Lincoln College. It's a huge school, so it's not similar in that way. There's 40 to 45,000 students at Virginia Tech. But it does have a very active School of Agriculture, schools of engineering, a School of Veterinary Science, and it's also set in the countryside in the same way that Lincoln College is as well. Just a few things about Lincoln College, Virginia Tech. A lot of the buildings are made of this substance called Hoagie stone. It's a kind of limestone, I guess. Here's our school mascot. It's called the Hoagie bird. We think it's a turkey, but we're not really quite certain. And it's got a beautiful campus, largely due to the stone that it's built out of. And of course, do we have some sound there? This is Lane Stadium, the college campus stadium. Now the team runs on to Metallica in every game, and you can see the students bobbing up and down. I thought the pogo was dead in the 1970s, but apparently it's alive and well as the Hokies run on to Lane Stadium. And as you can see, it's absolutely huge. 65,000 people, regularly attend a college football game, which is quite incredible. Okay, so here's where I work. At the medical campus of Virginia Tech, you can see that it has some of the Hokie stone in its base. The boss actually wanted to make the whole building Hokie stone, but then he found out how much it cost, and he thought, well, we'll just put it around, a nice trim around the bottom of the building. We're a relatively new campus. We've only been in place for 15 years. And anyway, it's been a great place to work. And here's some disclosures. As Sue mentioned, one of the things I do basic research, but I also translate it to startup companies. And so here are a few of the companies I'm associated with. I also just want to say quickly thanks to my lab. Of course, they do all the work. My main job is to beg for money. But they're actually the ones in the lab labouring over the experiments. I'm truly grateful for all the work that they do. Okay, the topic area of interest. So this is a plot of the causes of death in the United States over the last 120 years or so. And you can see that heart disease and cancer are big causes of death. There's been a little bit of improvement of late. Also, you'll notice here there are some COVID deaths in the 2020s and so on. But nonetheless, heart disease and cancer are major killers. Just in terms of raw numbers, over 500,000 people per year in the United States will pass away from cancer or heart disease, and around 150,000 or so will pass from stroke. In New Zealand, you can see the equivalent numbers up there. It's about 10,000 people per year for cancer and heart disease, and around 3,000 for stroke. So in this talk, I'm going to sort of describe some of my work, the work that my lab is doing, in an attempt to understand these diseases, but also to try and develop therapies that may be able to address them. Okay, so this is my little joke. The heart is an electric organ. It's not really an organ, it's kind of more like a drum, right? Because it beats away. And it's skilled at converting electrical activation to mechanical pump function. And as you all know, the electrical activity can sometimes go wrong. and we have what are called arrhythmias. The one that's been shown up there is a model depiction of a condition called atrial fibrillation, where the small chambers of the heart start to quiver. And in most people, it can be benign, but as we know, it can also be deadly, because blood clots associated with atrial fibrillation are a prime cause of death from stroke. So addressing these particular types of heart conditions is an important concern. So what is it that I do? Well, in that electrical activity, one of the structures that are shared between cells that's very important are these intercellular junctions. You heard me mention them in reference to Stan Bullivant. And the structure that I've been most associated with working on is a structure called the gap junction. And it's basically channels that are embedded in the membrane of one cell that link to a channel in the neighbouring cell. And basically they allow information, small molecules, to pass from the inside of one cell to that of the neighbouring cell. And so an analogy to think about it is they're kind of like the tissue's internet. They provide a framework for the passing of information between cells. Now, here's another depiction of the structure, the gap junction. Here's the membrane of one cell, the membrane of another cell. And when you see them in nature, they occur as clusters of these channels. And here you can see we've cut away one of the channels, and you can see the pore or the conduit which links the two cells together that allows small molecules to pass. Now, in typical Gourdie fashion, I've spent most of my career not studying the gap junction channels per se. What's caught my attention is what's going on at the edge of the gap junction, because this is where the structure is actually built. And what you can see here, and this is work that we've carried out over the last 20 years or so, the undocked channel from one cell is held in place, or scaffolded, as we call it, by protein-protein interactions, in this case with a molecule called ZO1, which links it to the actin cytoskeleton. And this association regulates the rate at which these channels move into the gap junction and then dock with their neighbouring cells to form these channels of intercellular communication. And there's some papers that we've published on this. This domain next to the gap junction, we've actually given a name. We call it the perinexus. And this young man here, Matt Rett, was a graduate student of mine. And he's actually with me the co-namer of this specialised domain of membrane that we worked on. Really, the identification of the perinexus kind of sealed my fate for about 15 years. Here you can see an image of a gap junction, this cluster of gap junction channels in green. We've labelled it with a special fluorescent dyes. And then around it, this beautiful halo of this molecule, the scaffolding molecule I mentioned, ZO1. And the work we've done on the perinexus relates to both the electricity of the heart, which I won't talk about this evening, but I'll talk about in another talk tomorrow, I believe. But also the role of this domain in injuries, and in particular the constituents of the perinexus, molecules like ZO1 and connexin 43. And that's what I'll be focusing on here. All right, so this is me back in 1991. You may be asking yourself, how did I get from wool fibres to Lincoln College and then to gap junctions, actually in a postdoctoral work in London. And it was via this gentleman here, Colin Green. Colin was the PhD student of Stan Bullivant. And when I came to the end of my PhD at Lincoln College, I wrote to Stan and said, hey Stan, I'd like to work in cell and molecular biology. Do you know anybody who'd want a postdoc? And so Stan wrote to Colin and said, give this young guy a go. He's got a knack for making experiments work. And so that really got me out of the wool field and into the gap junction field. So I'm grateful again to Stan and also to Colin and my other supervisor at the time, Nick Severs, who both had great influences on my subsequent career. Now, the therapeutics that I work on are based on what are called peptides. And peptides are essentially small parts of protein. They're made up of short chains of what we call amino acids. And you can think of the amino acids as kind of like Lego bricks. And when you stick them together, and in this case here, you can see these linear chains of Lego bricks, we call this a peptide. And familiar peptides that are currently in therapeutic use, of course, include naturally occurring peptides such as insulin, and also GLP-1 agonists like Ozempic are other examples of therapeutic peptides. Now, I know this is a little bit sort of arcane and difficult to understand, but this is a building block of the connexin channel. It's called connexin 43. And what we did was we took the domain of connexin 43 that's responsible for binding to the scaffolding molecule ZO1 and synthesized a short peptide based on it. And basically what we were doing was making something that would interfere with the interaction, get between the connexin 43 and ZO1 and separate it. And then we'd ask the cell biological question, what was the consequences of that? Did the gap junctions get bigger? Did they occur in different places? You know, we were making an experimental tool for basic cell biology research. And as shown up here, we made this short peptide in a couple of forms, including this version up here. We linked it to another peptide, which enables it to get inside cells, because that's where the target of the peptide was. But we also found that there was activity within this domain itself. So the point here is that when I first started doing this, we were just developing these as tools for basic science. Now, I had this young man join my lab at about this time, Gautam Gatnikar. Gautam had just completed a veterinary degree and a PhD out of NC State. So he was a clinician, a veterinary clinician, and he was interested in wound healing. And so he wanted to start putting our peptides on both simple and complex wounds. In this case here, we've got a lawn of cells that we put a mechanical scratch wound into, and then we watch the rate at which these cells move into that scratch wound. So it's a crude wound healing assay. And what we noticed was that this peptide sped up the rate at which these cells moved that healed this wound in the culture setting. He moved on to doing small skin wounds on mice and found that he observed something similar, that mice receiving the peptide showed a faster rate of closure of the wounds, but also reduced inflammation and slightly less scar tissue. So this suggested to him clinical implications. And in fact, he said to me, I don't want to be a postdoc anymore. I want to take out a patent and start a company to enable the clinical translation of this finding. So that's what we did. And in fact, they took, the company, in collaboration with my lab, took the peptide, alpha-CT1, through 3 phase 2 clinical trials and got positive results in all the trials. They were looking at both chronic wounds, such as diabetic foot ulcers, also venous leg ulcers, but also looking at it as a treatment to try and prevent scarring in surgical patients. And as I mentioned, returned positive results in each case. And I had a biomedical engineering student join my lab. We asked ourselves the question: what was what were the factors behind the improvement in scarring and in the indication where it reduced scarring? And we found that it was associated with an improvement in the organisation of the collagen scar matrix, and we published that a couple of years ago. So the company that we formed was initially called First String Research. But it was eventually purchased by a California private equity group, and they themselves just closed on a large deal with a pharmaceutical company. Now, I'm putting that up there as if to say, you know, I haven't seen any of this money personally, but some people have. But nonetheless, it was nice to see a therapeutic that we'd initially developed for basic science progress through these translational steps to be tested for clinical usefulness in patients. Now, as the company was moving forward with topical indications, i.e. the peptide was being put directly on the skin wounds, we were starting to look at other indications and other injuries that it might be useful in. And this is Jenny Jiang. Jenny did a PhD with me. She's now back in China. But she did very beautiful work showing that these alpha-CT peptides, as we call them, protected heart against ischemia reperfusion injuries. Now, ischemia reperfusion injuries are the type of injuries that commonly occur during myocardial infarction or heart attacks. So, you know, obviously a very serious wound to the body, and one that you know, causes a lot of morbidity and mortality. Now, the way she did it was we can take hearts out of mice, string them up, perfuse them with an oxygenated solution, and then they keep beating on this apparatus. And she put a tiny plastic bag the size of like a matchstick head inside the left ventricle. And with that tiny plastic bag, we're able to measure the contractions of the heart. Then what she'd do would be to turn off the flow of the oxygenated solution, so the heart would become ischemic, and you can see it stopped beating here. And then after 15 or 20 minutes, turn the perfusion back on again. And you can see that the heart resumes beating, but it's beating a lot less intensely. This is because a great majority of the heart muscle has been killed by the ischemic injury. Whereas hearts that had received our peptide prior to the ischemic event, you can see after the 15 minutes of ischemia, they kick back into life quite dramatically. So we call this a cardioprotective agent. The drug was basically protecting the heart against the ischemia reperfusion injury. But there's a problem. This is an isolated heart, and the peptide works for that. We put the peptide on skin wounds in humans, but it's topical, it's on the outside. The issue is that we can't give the peptide internally because the peptide are basically unstable. Once they hit a fluid like blood, for example, they break down within minutes. And so we discovered this. This is my friend and colleague at the veterinary school in Blacksburg at Virginia Tech, Jia He. And Jia placed our peptide in isolated blood and also injected it into animal models to look at the lifetime of the peptide in that situation. And literally the peptide breaks down within minutes, which is not long enough for it to have a therapeutic effect in a living animal. So this got me thinking about, you know, how do we protect the peptide when it's inside the body? And so we tried a number of things. We tried nanoparticles, which are popular, but they didn't work in our hands. But I started reading about these tiny vesicles that are released by nearly every cell in the body called exosomes. They're tiny lipid-bound vesicles, and they're about the size of a COVID virus, 100 nanometers across. But cells, as I say, all cells release them, and they're used in long-range signaling between cells. So they'll spit out one of these little bubbles, and it'll wander through the body and get taken up by another cell and transfer information to that cell. So in that way, you can still see I'm in intercellular communication. I'm not in direct intercellular communication if I'm moving into exosomes, but nonetheless, it's a similar concept. Now, the other thing that I realized was, and you know, not just me, but major pharmaceutical companies, was that these exosomes could be used to protect fragile but useful drugs when they're inside the body. They're also non-immunogenic. They don't invoke immune responses, which is something like nanoparticles often do. They can also cross hard-to-cross tissue boundaries. You might have heard of the blood-brain barrier. Very difficult to get across. Well, Mother Nature has endowed many classes of exosomes with the ability to jump right across that barrier and to go to the target where they need to go. And so if you think of the gap junction as the cell's internet, exosomes are kind of like the FedEx service. All right. Initially, we started off extracting exosomes from cultured cells, but I can remember one day in the lab with my lab manager, Jane, looking at a tiny pellet and saying, this is never going to work. We're never going to get the pharmaceutical industry to be convinced to make these things in bulk. This is just too hard, too expensive. Well, she shoved a couple of papers under my nose and she said, it looks like milk has a lot of exosomes in it. And I said, perfect, that's where we're going. And so the other nice thing about milk exosomes, I talk about Mother Nature, i.e. natural selection, milk exosomes have been designed to be orally ingested because, of course, it's all about passing information between mother and baby. And so, when you ingest milk exosomes, and what I forgot to do today was I meant to bring a bottle of milk in, and at this point I would have picked it up and drunk the milk and said, look, I've just drunk 3 trillion exosomes and I'm still standing here, but I forgot, I'm sorry. So they're very good for oral ingestion. But there is a problem when we're dealing with them. They don't sort of float around in milk like tiny little spaceships. They're actually tethered to milk proteins, and casein in particular. You've probably heard of casein, right? Well, here's an electron microscope image. And if you look carefully, you can see each of these exosomes is tethered to one of these strands of milk protein. So we had to figure out a way of separating those from the protein matrix that they were bound to. We did that by using a molecule called EDTA, which broke up the casein. We also avoided using ultracentrifugation, which is a separation method where you spin things at very fast speeds. The main reason we avoided it is because you can only do very small volumes, and we wanted to scale to industrial levels eventually. So we based our technique on filtration using a method called tangential flow filtration and also Sephiro's column filtration. And eventually we ended up with concentrates of these exosomes from milk that look something like this. Each one of these little bubbles here is one of our exosomes. Just what's astonishing is that these milk exosomes, we've estimated, account for about 10 to 15% of the volume of milk. So if you're drinking a lot of milk, it's probably a miracle you're not wandering around mooing, because you're taking a lot of cow information in, I can assure you. And just the numbers are astronomical, absolutely astronomical. In a litre of milk, there's a quadrillion exosomes, and I put this slide in just again to emphasise the sort of astronomical numbers that we're talking about. Okay, so we were working at lab scale, which meant that we were starting with a litre of milk, but we wanted to go to industrial scale. And so the postdoctoral fellow, who I forgot to mention, Spencer Marsh, he's been so important in this work, I sent him down to New Zealand. And he went to Massey University and worked with this gentleman here, Professor Richard Archer, who's now Emeritus Professor of Dairy Science at Massey. And also very generously, Fonterra gave us a tanker of milk, which we got cost-free, which was just great. So here is the tanker of milk arriving from Fonterra in Palmy. And this is the pilot plant that Spencer started to process the milk in 300-litre batches. He eventually got it down. We lyophilized that milk, which meant freeze-drying it. And he went back to the United States with 5 kilograms of fine white powder, which, as you can imagine, is a bit of a problem getting through customs, but nonetheless he made it. I mentioned lyophilization, and this is a paper we just published a couple of months ago. undertaken by, much of the work undertaken by a very talented medical student in my lab, Alan Dogan. But Alan identified this particular amino acid here, tryptophan, as very important in stabilising the exosomes during the lyophilization or freeze-drying process. So now we're able to produce our exosomes at scale. We're able to produce them at high purity. The next thing is, how do we get our peptide inside them? Because, they are membrane-bound vesicles, and traditionally, for 3.5 billion years, it's been a problem to get across a membrane, particularly for a highly charged molecule like a peptide. But to do this, we took a clue from something that we'd observed. This is a dye molecule called calcine, and it's got what are called ester groups on it, hydrophobic or soapy side chains that allow it to get through the membrane. And once it's through the membrane of cells, there are enzymes called esterases which clip off this ester group, trapping the glowing molecule inside the cell. So, where is it? There we go. So here we can see the uptake of this dicalcine within our exosomes. Again, stars in the sky. But basically, what it was teaching us is if we could modify the molecule with one of these ester groups, then we were able to get the peptide inside the exosome. And so that's what we did. We worked with a talented chemical engineer, Rachel Lettieri at the University of Virginia. She converted side chains on our peptide with these ester groups. And I know it's a lot, but we were able to use a fluorescently tagged version of the peptide and find that at a 100 micromole concentration, we're able to get about 85 to 95% of our exosomes loaded using this approach. Now, so we've got a peptide inside an exosome. We've got a proto-therapeutic in hand. Next thing we wanted to do was test it in a natural injury model in vivo. So these are two colleagues, also at the University of Virginia, Antonio Abate and Stefano Toldo. Stefano is expert at giving mice heart attacks. So we sent freeze-dried exosomes loaded with our peptide to Stefano, and he orally administered them in 100 microliter doses by oral gavage into the mice, gave them the heart attack, and then we took a look at what the result was. So these are slices through a heart, and what you can see here is a slice through the ventricle, the main pumping chamber of the heart, and this white slash here is the actual infarct, 24 hours after the injury has been delivered. And you can see it's a big old part of the heart that's now dead. Similarly, if we gave the mice unloaded exosomes, you can see that there's also a large infarcted area after Stefano had delivered the insult. But if we give mice exosomes loaded with our peptide, then there's virtually no white area. And we measured it, or they measured it, because they actually did the staining and quantification. And there's about a 60% reduction in the size of the infarct if the mice received these exosomes loaded with this peptide. So this was very encouraging. We also undertook some echocardiography studies on the mice to measure heart function, and this was also significantly improved by treatment with the exosomal therapeutic. I'll skip the last bar graphs there. Now, that study was done by oral gavage of the exosomal therapeutic right after the heart attack was delivered. But of course, if Granddad has a heart attack in the middle of the night and he doesn't tell Grandma about it until, a couple of hours later, it's often a while before you actually get to the emergency room. There's a window where therapy needs to be applied, and if it's left too long, then the damage can be permanent. But, people don't turn up in the emergency room within 5 minutes of having a heart attack. So one of the next set of experiments that we did was we delayed the delivery of the therapeutic. And we found that we could delay the therapeutic up to 2 hours after the heart attack and still get a significant reduction in the severity of the infarct. You can see when it's given directly after the infarct, it's about a 60% reduction. If there's an hour delay, we're getting still about 60% reduction. There's a little bit of a loss of that efficacy with the 2-hour delay, but nonetheless, when we measure it relative to the control group, we're still saving a lot of heart muscle. And of course, we measured the cardiac function using echocardiography and found that it was improved by these delayed treatments. Now, one of the most interesting aspects, and this is a little bit hard to follow, so I'm going to slow down a little bit, but when we give the exosomes by oral gavage, what we find is that there's a tropism, there's a homing towards the injured tissues, which if you think about kind of makes sense. You know, if mom was delivering information to baby, then she'd probably want that information most efficiently to be transferred to where the trouble's at. And we find the case, and obviously babies don't often have heart attacks, but nonetheless, when we label our exosomes before oral gavage with a fluorescent dye, we found that in the injured heart, they were being taken up in huge numbers, much higher than areas of heart muscle away from the injury site. Now, interestingly, when a heart attack happens, a molecule called ATP gets released by the cells. ATP, of course, many of you probably know, is important in the energy balance of cells, but it's also a very important immunological signaling molecule. And if it gets into the outside, it basically tells immune cells and such that trouble is going on. Well, we treated the animals with an enzyme called apyrase that got rid of the ATP, and lo and behold, the increased uptake that we were observing in the infarcted areas basically went away. So what we think is happening is that ATP is modifying the exosomes to make them more likely to be taken up in the injured tissues. And we've done a number of experiments to follow this idea up. I won't go into those experiments tonight, but nonetheless, and here's the quantification of that effect. Interestingly, we also looked at the skin wound to see whether there was evidence of injury-associated uptake in the skin following the surgery. And sure enough, there's a jump in the uptake of exosomes in the injured skin. Not quite as dramatic as you see in the heart, but nonetheless significantly higher. And again, if we get rid of the ATP, then we knock down that increase in uptake. All right. Okay. So moving along, I'm going to hit radiation injury in a second. So here we go. So I'm taking us back to Gautam, talented young man, and I give him credit for this discovery, but he intuited that one of the most responsive injuries to these peptides, these based on the connexin molecule, the alpha-CT peptides, might be radiation injury. And so he undertook a model with skin burns. In this case, again, it was using the alpha-CT peptide, not in exosomes, and he indeed found a very dramatic improvement in the response of the animal to radiation burns. So I took a look at this and I thought, okay, that's interesting. We know that radiation side effects are important problems with cancer therapy. Radiation therapy, of course, is one of the most important treatment modalities that doctors have for treating cancer patients, but many of them suffer from side effects, not just to the skin, but also to internal organs. And I thought, well, if we could transfer this effect that Gautam's seeing in the skin to the inside of the body, then that would be very helpful. The other thing, of course, is we don't have anything that mitigates high doses of ionizing radiation. People in the case of a nuclear attack or accident talk about handing out iodine tablets, but they're basically a placebo. What we need are drugs that mitigate the effects of high doses of radiation. So there's a military strategic need for such a unmet need for such a medication. So we worked with another colleague at the Virginia Tech Veterinary School and subjected groups of mice to lethal doses of radiation. And just very quickly, you can see in the control groups that these mice expire by about 7 days, whereas the mice that were receiving our exosomal therapeutic by oral gavage were surviving at a remarkable 42%. We also looked at radiation-sensitive tissues, including the gut and the bone marrow, and found that strong evidence of preservation of these tissues following treatment with our therapeutic. And in fact, we had the tissues graded by a veterinary pathologist, and she distinguished in a blinded way that the treated tissues, the gut from mice that had received the treatment were indistinguishable from non-irradiated controls. So through the generosity of a research foundation in New Zealand, the Red Gates Foundation, we received money to undertake actual clinical trials. We went to the FDA, and of course there's no way you can do a study of lethal radiation on humans. The FDA has a special pathway called the animal rule, where you can get approval for a drug by undertaking experiments on animals. But of course, you can't undertake those experiments yourself. You have to have it undertaken by an independent research organisation. And the Red Gates Foundation funded our study. And so it was a blinded, randomised controlled trial. There were 6 doses around our standard dose, around 20 animals per group, balanced for males and females. The amount of radiation was slightly less in the study that we did in our own hands. It would result in about 70% lethality over the 30-day study period. And I can tell you, in the lead up to this experiment, which we had no control over, I was very nervous. When you hand over, we handed over the exosomal therapeutic to Lovelace, the contract research organisation that was undertaking the work, and said, here it is, we've done our best to do the quality control checks, it's all good, please don't mess up this experiment. Unfortunately, because, it's basically, $500,000 you've paid them to undertake the work. So fortunately, it worked out. In fact, one of the doses, we saw almost 100% survival in one of the treatment groups. So we were very pleased with the results. And so we're going on to undertake some further studies, a phase 1B study, where we're going to be looking at repeated dosing and different timing regimens. And then the optimised dosage and regimen will be taken forward into a phase 2 clinical trial in pigs. And assisting with this work is a new company that we started called the Tiny Cargo Company. Here's its logo. And the principals in the company include Spencer, my former postdoc, also my brother Alan, who resides in New Zealand. He's agreed to be our CEO. He's in Japan at the moment, otherwise he'd be here. If he wasn't here, he'd be in trouble. But anyway, he's been very good in mentoring Spencer in the business aspects of the startup company. The company's just finished raising a $4 million seed round, and we have a number of very talented individuals associated with the company helping the translational progress forward. And including the building of a clean room where we will hope to be able to produce exosomes for our clinical studies and also for commercial use at industrial scale. And we expect the clean room to be commissioned sometime early next year. So with that, that's the end of this particular story, and I'd be happy to answer any questions that you may have.
Thank you very much, Robert. That was incredible. That was a whole heap of work explained in 45 minutes. Yep, so, yep, very well done, because complex work as well. So we are ready to take question and answers. If people have a question for Robert. I'm sure somebody has a question about the heart. Who's going to go home and drink a litre of milk?
There's more in raw milk than there is in pasteurised milk, by the way. So,
I was just wondering, do you see this new treatment as being something that people might take as a as a kind of preventative in a way, or do you see it purely as something that people would take, if they thought they'd had a heart attack or they thought they might be in the middle of having one?
yeah, that's an interesting question. We don't really know what the consequences of repeated dosing are. We're just giving it at the moment as a single acute dose around the time of heart attack. But just to broaden out your question a little bit, Sue mentioned right at the beginning that milk exosomes are almost the perfect drug delivery device. So we're putting our peptide inside them, but basically they can be used to deliver anything. So one of the things that we're excited about is to get gene vectors inside them, expression constructs. Because if we can do that, at the moment that's done by, you might have heard of using viruses to deliver genes for gene therapy. There's a whole lot of problems associated with that. There's been deaths, people have immune reactions. In fact, about 70% of the population has virus neutralizing antibodies, so they don't work in those individuals. Milk exosomes, by contrast, fly under the immune radar. They can be taken orally, and as I mentioned, they go where the trouble's at. So, we think we might have a means of, if we can figure out how to get the plasmids inside the exosomes, of delivering gene therapies using this approach. And when I say it's no small thing getting a DNA expression construct inside through the membrane inside these things.
Thank you.
But hopefully we'll figure it out.
Hi, Rob. I'm not sure whether this is appropriate to what we were talking about, but we touched on the heart. How far are we away from being able to remove calcium build-up in the arteries in the heart? Is that your field?
Yeah, it's not exactly my area, but it is an area of active research. And again, because our milk exosomes basically home in on injured and diseased tissues, it may be that milk exosomes accumulate in plaques within arteries in a way that could be used to deliver therapeutics for those types of pathological circumstances.
Hi, thank you for your presentation. I'm just curious, for someone who has chemotherapy, how would this be very beneficial in helping them recover faster with fewer side effects?
Yeah, that question raises an interesting prospect because, basically, so we're talking about radiotherapy rather than chemotherapy, of course. But one of the side effects of being able to protect normal tissues against radiation is that the clinicians might be able to ramp up the dosage of the radiation on the actual tumour itself. And so, we're yet to test that in experimental models, but conceivably it could improve the efficacy of radiation therapy. And we have data, and I didn't share it with you because of in the interest of time, but we've actually asked the question, we've been asked the question in forums like this. So you're protecting normal tissues, but what say, you also protect the tumour? And so we've undertaken some number of experiments where we've, given mice tumours and then asked the question, does our therapeutic also protect the tumour? And interestingly, it doesn't. And so, you know, we're very excited about that result, and that's one we'll be following up in future research.
It seems quite an important part was your being able to stabilise the exosome so that it had a shelf life of 12 months. Where did that idea come from, or the implementation of that?
Yes, so it partly came out of our association with BARDA, which is a biodefense organisation. It was very, in the United States, that was central to the distribution of COVID vaccines. You know, and as we know, one of the big problems with the COVID vaccines, especially the mRNA vaccines, was they have to be held at minus 80 degrees Celsius. And it just means that the supply chain is very restricted. And so BARDA, in our conversations with us, were saying, you know, we don't want something that we have to store at minus 80 degrees. We want something that, you know, is stable for long term and stable at room temperature. And so that's why we embarked on the drive to figure out how to freeze dry the exosomes. It kind of came out of COVID.
Something good to come out of it.
Yes.
Is there a question
I just want to say thank you for a most interesting presentation. My query is, New Zealand milk, do we produce the best exosomes? And is New Zealand milk going to be, is our milk superior or as good as? And does New Zealand milk still have a role to play in what you're doing through Tiny Cargo?
Yeah. I don't know if we have the best, maybe we've got the best cows. Although I don't know about that, having spent some time in a milking shed. So, I think, so Fonterra was very generous to us in providing us with milk, and we started to work with them to try and get their interest in helping us along this journey. But we think that, milk exosomes potentially are, a very important component of milk that could be extracted and used by the industry. For example, baby formula. Baby formula is produced by air drying milk at 200 degrees Fahrenheit, which absolutely destroys the exosomal component. And so one of the things we've been thinking is that if we can figure out how to isolate exosomes and add it back into baby formula, we might have a path to providing the information that was lost during the traditional methods used to produce baby formula. And there's a growing body of research that suggests that these exosomes in breast milk are important in bone development, in immune development, and also neural development. The very interesting study where one group in Canada fed rat pups milk with exosomes in it versus milk that had been depleted with exosomes. And the rat pups that received the exosomes solved maze puzzles 9 times faster than the rats that didn't. So, I think there's a lot of work still to be done, but I think, there's a real opportunity for New Zealand to take advantage of this, because, what is New Zealand? It's now a huge dairy farm with beautiful beaches. It's a major industry, and I think, this is an industry of the future.
Robert, thank you. And during your inspirational mentionings, it took me back to my childhood raised on a farm where, as country school children, we drank milk daily, compulsorily, straight off the cows. It was so warm. That's how I knew it wasn't far from when it had been actually extracted. And then in my days, we had compulsory milk at school. I remember my childhood as being very absent-free of any ailments and illnesses. I'm just thinking in my mind, I wonder if there is a cohort of New Zealanders brought up on compulsory milk in schools who have a stronger cardiac outcome or healing potential. If there is also a case for bringing back compulsory or very strongly desired milk at school level to save the national health on potential future cardiac and other wound healing issues in older aged people. It's just a thought.
Yes, no, an interesting thought. And I remember those days as well, receiving a bottle of milk at Blockhouse Bay Primary. Yeah, I wish it had been chocolate milk actually, but anyway. But yeah, I'm not expert enough to know. I know that drinking of raw milk is becoming more and more popular. With industrial scale production of milk, there is problems because you're aggregating across huge numbers of farms and huge numbers of cows, and so care has to be taken to ensure that you're not propagating pathogens and so on. At the level of individual farms, if you know the cow, there's probably not too much danger, but for the industrial production of milk, there's more risks involved, I guess is probably the best way to say it.
Well, to wrap up now, so I'd just like everyone to put their hands together, please, and give a big thank you to Robert for a most incredible talk. And I'd just like to invite Donna Rose back up. Donna Rose, would you just like to join us up here? So I think we can all acknowledge the two incredible professors that we have had here tonight. These are world-acclaimed professors working in their field, and we're so lucky to have heard from them tonight. So please, another big round of applause to say thank you so much.
Thank you all.
Yep. I'd also like to thank the Auckland University of Technology for hosting this evening in this beautiful building, tukutuku, and for all of you for coming out tonight. It was lovely to have you all here, and also those joining us online. So I hope you go home inspired, drink milk, imagine. There's so much that you have to do when you get home. You won't be sleeping tonight. So, but tomorrow night too, both of our professors will be presenting at the University of Auckland, but they'll be more scientific. So it's more of a medical audience, but you're more than welcome to come along to that as well, 6 o'clock tomorrow night. So thank you very much, everybody, for coming. Thank you to our professors, and we hope to see you all again soon.
All right,
Kia ora. Thank you.